Hi folks, and welcome back to lesson 21 of the Dead Earth game development series brought to you by the Game Institute. In the last lesson we wrote our very simplistic idle state for our zombie, and we saw that when the idle state is transitioned into, one of the things that it does is it contacts its state machine and it sets its speed to 0. And we also saw that the state machine itself takes that speed value and passes it in as the speed parameter into Jill's animator. And we also saw many lessons ago, when first setting up the base layer of this animator that Jill is using, that we have transitions that say if speed ever drops down to 0, or in this case below 0.5, then whatever animation we're in, we're going to transition back to idle. Now if we select the idle state, we can see that we added to that a state machine behavior called the root motion configurator, which allows the animation state to talk to the state machine and tell it whether position and rotation information from the root motion in the animation should be used to update the character. Now in the case of the idle state, you can see that we are saying that when the idle animation is playing, we wish to use both root position and root rotation. And you can see that if I press play, that is indeed what is happening. You can see that Jill is very convincingly sort of moving left and right, and we can see the camera moving because the left and right motion is being used to kind of also alter Jill's position in the world. We also saw when we created our simple demos many lessons ago that when we're in the locomotion state, there's two ways that we can do it. We could either do what we originally did, which is create a two-dimensional blend tree and contain in that blend tree not only the running forward animations but also all of the various turning animations, and then have the turning arcs of our patrolling zombie controlled directly from the root motion in the animations. But we saw that this presents problems with accuracy, and unless we had a very large selection of different turning animations, we saw Jill would run into walls or overshoot her mark. So what we decided to do instead was use the second method that we discussed, which is where in the blend tree, and if I drill down into Jill's locomotion blend tree, in her blend tree we just have 3 forward locomotion animations: a walk, a jog and a sprint. And they are just in a one-dimensional blend tree, and they're controlled by speed. And you'll also remember that I said that we're going to use our own speed thresholds here. So if we set speed to 1, this is the speed that will be used. If we set it to 2, this is the speed that will be used. And if we set it to 3, then Jill will be in a full-blown sprint. The point here is that when we're in the locomotion state, you can see that the locomotion state has the root motion configurator script on it. But this time we set 0 for root rotation because we're saying there is no root rotation in our animation files. We're going to control that ourselves. So in the case of the patrol state, what this means is every frame in its update, we're going to kind of measure the angle between where our zombie is facing and its steering target, and we're going to rotate Jill smoothly round to keep her facing in that direction. Now the only exception to the rule is if we find that when we get to a waypoint we have to turn Jill so much that she would obviously spin on the spot, and that would be obvious for the player to see. Well then, when that's the case, when the steering target angle is greater than some threshold, like say, I don't know, 80 degrees, that's when we're going to drop out of the patrol state and into the alerted state, which is going to see zombie Jill turning left or right to kind of turn on the spot using root rotation. And then when that target is once again within its sight, we're going to go back into the patrol or the pursuit state. Now we know how that's going to work, let's create our patrol state. So in the assets folder, Dead Earth folder, scripts folder and AI folder, I'm going to create a new C# script, and I'm going to call this AI zombie state underscore patrol 1. And then I can't drag this onto Jill yet, because just like when we created the idle script, it's not a fully fleshed out class yet. We have some functions that we need to implement from the abstract base class. So I'm going to open up this in MonoDevelop and delete the boilerplate stuff. And once again, delete MonoBehavior as the class it derives directly from, because it derives from AI zombie state. And of course, like we saw before, we need to override the getStateType function, getStateType, and for that we will simply return AI stateType dot patrol. And we also need to override the onUpdate function. So I'll say public override onUpdate. And for now, once again, if we're in the patrol state, then we'll just stay in the patrol state. So we'll say AI state type patrol. I always like to do this first of all so that I can save the script off, go back to Unity, and then drag and drop that onto Jill. Because what tends to happen, and I know it sounds kind of dumb, but I'll often be working on a script, a state, and I'll be sort of pressing play and wondering why what I've done doesn't seem to be having any effect. It turns out I've forgotten to actually drag the state onto Jill to begin with. I know, a bit silly, right? But hey, I'm a silly man. Okay, so now we need to think about the properties that we're going to need to expose in the inspector so that we as developers can configure the patrol state. So I'm going to put a little comment here saying inspector assigned. And one of the things that we're going to need to assign to the patrol state is the waypoint network that we would like the zombie to follow. So remember, the waypoint network is a class that we have already created. It's called AI Waypoint Network there. And we've seen this being used in all of our earlier demos, and we've got some assigned in the scene actually, haven't we? Yes, we've got Waypoint Network 1 and Waypoint Network 2. I will assign Jill Waypoint Network 1, I think. So we will say we want to create a serialized field of type AI Waypoint Network, and I'll call this Waypoint Network. I'll set it to null by default. And then if we save that off and go back to the editor, you'll see in the inspector now for Jill that we now have a slot where we can drag a waypoint network into it. So I'm going to drag over waypoint network 1 and click save. So I think the next thing we want to do is add a Boolean variable that is going to allow the user to specify whether the zombie should be patrolling this waypoint network randomly or in the order in which the waypoints are specified in the waypoint network. So going back to our script, we'll do another serialized field of type bool, and we'll call this random patrol. And we'll set this to false by default because I think more often than not we're going to want our zombies to be following the exact waypoint route that we lay down. Actually, I'm not even sure that's true, but false seems a pretty good default value. Now the next thing I'm going to serialize, even though it's more of an internal variable really, is going to be the current waypoint that we are patrolling to. Now by default this is going to start off at 0, and we're going to start heading towards the first waypoint in the waypoint network. Now the reason why I'm serializing this in the inspector and not just making it a kind of hidden internal variable is that we may well want to, when we're setting up our zombies, place our zombies such that we know a zombie we've placed starts off much closer to the third waypoint in its waypoint network. So we might set its current waypoint to 3 at startup, so it runs to its closest waypoint. I suppose we could also add some functionality that examines all of the waypoints in the waypoint network and finds the closest one. Maybe we'll do that later. For now though, I'm going to serialize current waypoint, because even if we end up not using this to set the current waypoint via the inspector, I think it's going to be a pretty good thing to see changing in the inspector for debug purposes, so that as the zombie is reaching its waypoint and then it goes on to the next waypoint, we're going to see this variable increasing. So that's going to be an integer, and I call this current waypoint, and we'll set that to 0 by default. So the next variable I'm going to add to this class is going to be speed, because we want to be able to specify what speed the zombie should be patrolling at when it's in the patrol state. And this is cool because it means that each of our different states can have different speeds. So we can have the zombie that is patrolling using speed 1, the walking speed, but then when we write the pursuit state, we could say we want the zombie to use speed 2 or 3. So you'd see the zombie walking around quite leisurely, and then all of a sudden it sees a threat and it accelerates into a sprint. So I'm going to create a serialized field again. This is going to be, it's going to be a float, even though our speeds are essentially integers 1, 2 and 3, well, and 0. I make it a float because we may decide, we'll have to see how it plays out, but we may decide that when we're going from one speed to the next, we might want to sort of lerp between them over a little bit of time so that we have a smooth transition. I'm not quite sure yet. It might be that just the transitions alone in the animator are enough to give those smooth transitions. What should I call this? Speed or patrol speed? I think we'll just call it speed. Then we can use that same name in all of our states that we create. So I'll set speed to 1 by default. I think what I'll also do for speed is I think I will give it that range attribute. So it's a nice slider bar. 0, 3. Like so. Let me just go back to the editor, check that was all looking okay. So you can see now that in the inspector we have that nice slider bar for speed, which is easy to configure. Okay then, so let's now add to our patrol script the onEnterState function, which is going to, configure the animator and set all of the variables to their initial values so that the patrol state is initialized properly. Now, if I go back to my script, I've just paused the video and put some comments in there, which is why it may look a little bit different, but don't worry, I've added nothing else other than comments, and I think we're going to put the onEnterState right underneath the getStateType function. And in fact, what I'm going to do is I'm going to go over to my idle state that we developed in the last lesson, and I think I'm going to just copy that whole thing over, because although this onEnterState function is going to need to be different, there's quite a lot of stuff there that we can use. So I'll copy that over and then we'll start picking among the bones to see what we can use. Obviously we want to get rid of the stuff to do with the idle time and the timer, because that's not used by this class. And we also want to change that debug log to say entering patrol state. But as we're going to do with all states, we do want to call the base class implementation. We do want to check that the state machine is valid, and if not, then simply return. And we also want to configure nav agent control for position updates only. We don't want the nav agent controlling our rotation, because it does pretty unrealistic rotations, to be honest. And we've already discussed how we're either going to control the rotation ourselves in our states by rotating Jill towards her steering target, or in the case of other states that use root rotation, we're going to be allowing the animation to control that. So we don't want to set speed to 0, we want to set speed to whatever we've configured it. So we'll say stateMachine.speed equals speed. We're not seeking, so we'll set seeking to 0. We're not feeding, so we'll set feeding to false. We're not attacking, so we'll set attack type to 0. Now, do we wish to clear the target? Well, this is an interesting point. Sometimes we do. Now, to understand when we don't want to clear the target, we have to remember how this is going to tie into the alerted state. We said that if Jill is heading towards a waypoint and somewhere along her path she has to do a very sharp turn, we don't want it to look like we're spinning her on the spot. So what we're going to do is we're going to temporarily drop out of the patrol state and into the alerted state. Now, when we transition into the alerted state, that waypoint, let's say it was waypoint 0, is still going to be Jill's target. So assuming no other threats come into her field of view, that's going to be a target that she is rotating left and right on the spot, trying to get in her field of view. And assuming she does get the target, then we're going to drop back out of alerted state because she's rotated round enough and back into the patrol state. Now, if we get into the patrol state, we still want to be heading towards that same waypoint. If we clear the target, then what's going to happen is the onEnterState function is now going to have to generate a new target waypoint, and that might be the next target in the list, or in the case of a random waypoint selection, because remember we also have that boolean that allows us to select waypoints randomly, we could see Jill shoot off to a completely different waypoint. So what we really want to say is we only wish to clear the target if the current target that is set is not a waypoint. If it is, then it means we're kind of in the middle of heading to a waypoint, so we probably shouldn't clear the target. But if it's anything else, then we will clear the target. Now you might think, why would we clear the target at all? Because the target might be something like a player threat or a sound or something like that that has much higher priority than a waypoint. But it doesn't matter, because as soon as we drop into the onUpdate function, we're going to assess all of the threats anyway. So if in that very first update we find that there's a more compelling threat, then we're going to transition out of patrol into pursuit or alerted or whatever. So what I'm going to say is I'm going to say if the zombie state machine, and what I want to do is I want to get the type of the target that is currently set. However, I do not believe that I've actually added a getTarget type to the state machine base class. So I should probably do that now. Overlooked that, didn't I? Actually, I'll write the code in here, but obviously we haven't implemented the function yet. So it's going to be red in MonoDevelop. So I'll say getTarget type equals AI target type dot waypoint. Actually, I want to say doesn't equal waypoint, then we clear the target. Okay, so we get the type of the target that's currently set in the state machine when we transition into this state, and if it's not a waypoint, then it's something else. Let's just clear it for now so we get a nice clean start at entering a patrol state. But we need to add this get target type function now to our base state machine class. So let me go back to Unity, open up our AI state machine class. Actually, I'm going to make this a property, not a function, so I'll just call it target type, like so, with a getter that simply returns the target's type. And of course I'm going to have to go back to my patrol state because I thought I was going to write a function called get target type, but I'm not. I made it a public property instead called target type. There you go. Now we're in business. So let me just go back, check we've got no errors. Okay, so if we're currently heading towards a waypoint, then we're not going to do anything. But if we aren't heading towards a waypoint, if we don't have a waypoint set as our current target, then we're going to clear the target. And what we're going to do is we're going to fetch a new waypoint to head towards from our waypoint network. And we also need to factor in that if we've set to do a random patrol, then we fetch this randomly from the waypoint network. And if we haven't got random patrol set to true, then we're just going to increment the current waypoint so it moves on to the next waypoint in the list. So assuming we have a valid waypoint network, and assuming of course the waypoint network actually has some waypoints in it, then we're going to step into this code and we're going to fetch a waypoint. Now in the case where we're doing a random patrol, we'll just select it randomly. So we'll say current waypoint equals random.range 0, waypoint network dot waypoints dot count. Actually, I need to say count -1 because random.range is inclusive, isn't it? So if it's not a random patrol, then we're just going to, the current waypoint is going to contain the index of the waypoint that we want to head towards initially. So we might have set this in the inspector to 0. Okay, so only if random patrol is set to true do we override current waypoint with a different value. Otherwise, we just leave it how it's set in the inspector. And you're going to see later on that when we reach the waypoint, this class is also going to have a next waypoint function, which takes care of incrementing the waypoint counter to point at the next waypoint in the list. Okay, so now we want to fetch the waypoint from the waypoint network and basically check that it's a valid waypoint. So we'll say transform waypoint equals waypoint network current waypoint, like so. So you can see, remember, the actual waypoints in the waypoint network are just transforms. So we're just indexing into the waypoints array using our current waypoint to get the correct waypoint. Assuming this is valid, if waypoint doesn't equal null. Actually, I should probably just check there that current waypoint, for whatever reason, isn't outside the bounds of the waypoint array. Oh, I hate all this housekeeping stuff. But it does make your program explode in a controlled way when you get things wrong. So I'll say if current waypoint is smaller than waypoint network.waypoints.count, then we're going to step into this, because otherwise we've just got an invalid index and we're going to get a load of errors. Okay, so just to reiterate, we fetch the current waypoint if it's random, or we just use the one that's currently set in the inspector, and assuming the index is a valid index and we're not overstepping the bounds of the waypoint network's waypoint list, then we fetch that waypoint from the waypoint network list, and assuming it's not null, we are then going to set this as the new target for our state machine. So we'll say zombie state machine dot set target. In the previous state we saw us using set target, and when we called set target, you saw us using an overload of the set target function where we just passed it an AI target structure. But in this case, we're going to use the other variety of that function that allows us to pass in all of the individual components. So the target type that we want it to be, the collider, if that's applicable, and the position and distance. Because obviously our waypoints are transforms, they're not target types. So we're essentially using this function so that behind the scenes in the state machine, this is going to be constructed into an AI target structure. So for the target type, we'll pass AI target type dot waypoint. For the collider, we'll simply pass null because waypoints don't have colliders. For the position, we will simply pass in the waypoint dot position. Remember, waypoint is just a transform. And for the distance, which is the fourth parameter, we will simply use vector3.distance. Actually, let me just move these onto separate lines here so we can see things a little bit more clearly. That's better. So as the fourth parameter, we'll pass in vector3.distance, zombie state machine, transform.position, and waypoint.position, like so. So we've told our state machine that we've got a new target, it's a waypoint, this is the position, and obviously this is the distance to the waypoint, which the state machine is then going to keep track of in its fixed update with each tick of the physics engine. But what we haven't done yet is told the nav agent that this is where we want to go so that it can plot a path. So we will use the state machines, zombie state machine dot nav agent, because remember nav agent is a property of our state machine, which allows us access to the nav agent, and we will use the nav agent set destination function, and of course we will pass in waypoint dot position. And then, just in case for whatever reason another state might have paused or stopped the nav agent from walking down a path, we'll just make sure that we call the nav agent's resume function. There you go, resume, like so. So just in case for whatever reason we kind of paused or stopped the nav agent, we're just saying we want you to do your thing again. We want you to start plotting your route and trying to navigate to this new position. Actually, I think what I'll do is I'll take the zombie state machine nav agent.resume line, and I'm just going to move that to kind of the bottom of this function so it's outside the conditional that is only executed if when we go back into the patrol state we're not already tracking to a waypoint. So even if when we enter this state the target is a waypoint, for whatever reason, if the nav agent has been paused or stopped, we just tell it to resume. We shouldn't have to set its destination, it should already be set from when that target was initially set. So let me just put some comments in here. Okay, so I think that's our onEnterState function complete. So let me just very briefly go over this. So as we step into the onEnterState, we call the base class, we check we've got a valid state machine, and we configure the state machine so that we can pass the parameters into the animator. So we set the speed, which we know is going to cause the animator of Jill to transition from the idle state into the locomotion state. We make sure that everything else is set to off. And then what we do is we check the current target type that is set within the parent state machine. If it's a waypoint, then we don't really do anything because it means that we've probably just come back into this state from having previously been in a patrol state and then dropped into an alerted state, really just so we can use the route motion in the turn on the spelt left and right animations. And then we've aligned ourselves with the waypoint target, and then we've dropped back in to this state. So when that's the case, we don't really do anything. We just call zombie state machine.navagent.resume just to make sure that the nav agent is active and it hasn't been stopped or paused. However, if we're not currently heading towards a waypoint, then now is the time when we wish to now head towards the next waypoint in our path. So we clear any previous target. We check that we have a valid waypoint network. If it's a random patrol, then we just set the current waypoint index to any random number between 0 and the number of waypoints in our waypoint network. And then assuming that we have a valid index, it's within the range of the waypoint network, we fetch that waypoint from the waypoint network. And assuming it's not a null transform, we set this as the new target, passing in null as the collider, because waypoints, like other threats, don't have colliders, passing in the position and passing in the distance from ourselves to the waypoint. And then underneath setting the target, we then just get the nav agent that our state machine is using, and we call it set destination function. And we know that that is going to plot a path from where the zombie currently is to that waypoint. Okay, so onEnterState function done. Now it's time to do, I believe, the onUpdate function where the magic happens. So the first part of the onUpdate function of the patrol state is going to look very much like the first part of this same function in the idle state, where we're going to assess the threats and possibly transition into another state should the need arise. So what I'm going to do, just to sort of speed this up a little bit, is rather than you just watch me laboriously type out each conditional, is I'm just going to copy and paste them in, and then we'll talk about them as I add each one. So first of all, we check, just like we did in the idle state, if there is a visual threat, is that visual threat the player, which is the highest priority threat? And if it is, then we set that as the state machine's new target, and we return AI state type pursuit to transition into the pursuit state, which we know is going to be the state that is going to have the zombie running toward the target. So next up, we check if it's the player's light. So we say if the visual threat is of type visual light, then set this as the target, but this time we return, just like we did in the idle state, AI state type alerted. Now remember, we do this because when it's a light source that is the visual threat, then it means that this light is obviously shining on the zombie from outside of its field of view, so the zombie doesn't really know, or isn't supposed to know, the exact position of the threat just yet. So it goes into the alerted state with this set as its target, where it's now going to be turning on the spot left, turning on the spot right, trying to get that visual threat within its field of view. And then if it does, then the alerted state will transition into the pursuit state, and it will behave very much like the clause above it. So next up, we're going to deal with the case where it is the audio threat that is set. And of course, because we check these in a very specific order, we know if we get here and we're checking that the audio threat is set, then we know that's because these two cases up here were not true. So in that case, we handle it just like the light. We set the position of the audio source as the target, and then we go into the alerted state so that the zombie will try turning on the spot left and right, trying to get the position of the audio source within its field of view. And if it manages to do that, then it will transition into the pursuit state and behave much like the very first case here, where the zombie will just run towards the sound source. Now, in the case where the visual threat is food, we do something a little bit differently, and we use the satisfaction member of the zombie state machine to put an extra bit of filtering in. Now, what we're essentially trying to do here is we're trying to say, based on how hungry the zombie is, how far is he willing to come off his patrol route to pursue food? So if he's only a little bit peckish, then if he sees some food but it's a long way away, he might think, I'm not going to divert off my path to do that, I'm going to carry on my patrol route. But as the zombie becomes more hungry, or becomes less satisfied, he's prepared to travel greater distances to get to that food source. So the way that we do that is we step inside this conditional here if the visual threat is food, and then we take the zombie state machine's satisfaction member. Now remember, this member is a 0 to 1 range value, where 1 means the zombie has a full belly and 0 means he's got a completely empty belly. So 0 means he's really hungry, 1 means he's not hungry at all. So I flip this and I say 1 minus satisfaction factor, so that the result of this argument here is a 0 to 1 range value that describes how hungry we are. 1 very hungry, 0 not hungry at all. So then what we do is we take the distance to the threat and we divide it by the zombie state machine's sensor radius, but we're just trying to create a 0 to 1 range kind of normalized distance value, okay, where 1 means that the visual food is right at the very outskirts of the sensor trigger, and if we get close to 0, it means that the food source is very close to the zombie. So now what we have is we have this inverted satisfaction factor, which now describes hunger in the 0 to 1 range, and we have the distance within the sensor radius to the food threat in the 0 to 1 range, and we simply say if our hunger is greater than the distance to that food source, then we are going to drop into the pursuit state and we're going to set this food as our new target. So that's basically all the threat assessment code done. What we have to do now is write the code that actually processes the patrol state. Now the thing to remember is that in the patrol state, we're going to be in the locomotion state in the animator, where we're not going to be using route rotation, which means we're going to be responsible for rotating Jill's transform ourselves based on the angle between where she's facing now and the steering target. What we're going to do first of all is we're going to measure the angle between where Jill is now and where she is supposed to be facing. And then if the angle is, let's say, larger than 80 degrees, then we know that turning Jill through that wide arc is going to be very visible to the player that the zombie is spinning on the spot. So what we'll do in that case is we will drop out of the pursuit state, We'll still leave the waypoint as our target, but we'll drop out of the pursuit state and into the alerted state. And this is going to set the speed to 0, which is going to drop us back to idle. And the alerted state is also going to set seeking to either left or right, which is going to then activate either the zombie turn on left or the zombie turn on right animations. So this will allow us to have Jill come to a stop, kind of turn on the spot to more correctly face the direction she's supposed to be heading, and then she will then transition once again back into the locomotion state where she'll start running toward the waypoint again. You're reminded that when we're in the zombie turn animations, we are using route rotation. That's the whole point of us doing that, so that when we get to the point where rotating Jill too much would cause such visible sliding, we go into this alerted state that allows us to use route rotation to turn Jill more convincingly. However, in order to execute this code, what we really need to do is we need a function that allows us to get the signed angle between where Jill is facing and where Jill wants to be facing. Now, Unity has the vector3.angle function that gives us the angle in degrees between two vectors, but what it doesn't do is give us a signed angle. So we want to know whether we need to rotate left or right. So I think what we're going to do, much like we did with the collider is visible function, is I'm actually going to make this a static class function of, where did I put it? Was it in the AI state or the AI zombie state class? It was the AI state class, wasn't it? Sorry, not the collider is visible function, as that was very specific to zombie state machines. It was the convert sphere collider to world space function, which we made a static member of the AI state class, so that it's just available for any class or object anywhere in our game to use. So I'm going to write the find angle function now. So this will be a public static function that returns a float, and I'm going to call this find signed angle, and it's going to take two vectors, the from vector and the to vector. So the first thing we'll do is we'll just make sure that the two vectors that have been passed in aren't identical to each other, because in that case we know that the angle is just 0 and we can return that straight away. So we'll say if from vector equals to vector, return 0. Next, what we'll do is we'll create a float that will store the angle in degrees between these two vectors using Unity's angle function. So we'll say angle equals vector3.angle, and then we're going to pass in the from vector and the to vector, like so. Now this gives us the angle, but we don't know whether we need to rotate left or right. So we're going to use the cross product for that, much like we showed quite a few lessons ago, how we can use the cross product for this purpose. So we will say vector3 cross equals vector3 and use Unity's cross function, passing in the from vector and the to vector. And if the y component of the returned vector is positive, then I think that means we need to turn right, and if it's negative we need to turn left. I'll have to just double check that. It may be that I have to switch the order in which I pass the from and to vectors into the cross product function. I'm never really good at remembering that. So we'll say angle, and we'll multiply angle by the mathf.sign. Remember, sign is a function that just returns either 1 or -1, depending on whether the value we pass in is signed or not. So we will pass in cross.y, the y component of the returned cross product vector. So if y is negative, this will return negative and will be basically multiplying angle by -1, exactly what we want. And if it's positive, it will return +1 and we'll be multiplying angle by +1. In other words, angle will not be altered. And then we just return the angle. And let me put some comments in there. I'll say returns the signed angle between two vectors in degrees. Okay, so that's that done. Like I said, if we find when we execute our code in a minute that the zombie's turning right instead of left or vice versa, then we know we just need to flip this around a little bit. So going back to our onUpdate function now of our patrol state, after we've done all the threat assessments, we're going to call that AI state find angle function. And we're going to say float angle equals AI state.find signed angle, which is that function we just wrote. And as the first vector, we will just pass in our forward vector. So I'll say zombie state machine.transform.forward. That's the direction that we're facing. And we want to measure this against another vector, the vector that we would like to be facing or that we should be facing. So for that, I think we can use the Zombie State Machine's nav agent and use its steer target. The steer target is the position that the zombie is currently heading towards along its path. Now remember, the steer target is not necessarily the waypoint, because if we plot a point to a waypoint, that waypoint may be down a path that the zombie has to do 3 or 4 left or right turns to get to that waypoint. So the targets are the individual waypoints that the pathfinding system plots along that path to the waypoint. Zombie State Machine nav agent, get access to the nav agent, and then of course the nav agent has that steering target property that returns a position vector describing where in world space we are currently heading towards. Now of course we can't just use that. What we need to do then is subtract from that the position that we're at, so that we've got a vector from our current position to that target. So from that we will subtract zombie state machine dot transform dot position, like so. Okay, so we now have our signed angle. Now what we need to do is we need to determine if the angle is larger than the threshold to drop us down into the alerted state. So I think what I'm actually going to do is I'm going to add an extra variable to our patrol class that allows us to actually set that in the inspector. So I'm going to create another serialized field of type float, and I'm going to call that turn on spot threshold. I think by default I'm going to set that to 80 degrees. So going back down to our update function, we will say if mathf.abs, we'll get the absolute value of angle here. Ironic, isn't it, considering we wrote that function to deliberately get the signed angle, is larger than the turn on spot threshold. Then we're going to drop out of this state into the alerted state. So we will say return AI state type dot alerted, like so. However, if we haven't dropped that into the alerted state, then it means that we are going to stay in the patrol state. The angle that we're supposed to be facing is not too far away from where we're currently facing. So what we're going to do is over time gently rotate Jill's transform so that she acquires that new heading. Oh, by the way, you may be wondering why we implemented the signed angle function at all when we just do an ABS on it. It's a very good point. In fact, we don't really need to use this function until the alerted state. So actually, I think I'm going to change my mind and I'm not going to use that function here. I'm just going to use the vector 3 angle function. No point using that function if we don't need it. But don't worry, we will see the signed angle function being used in the alerted state. So we get the angle between the direction we're facing and the direction we want to be facing. If it's larger in degrees than our turn on spot threshold, then we drop out into the alerted state. But if that's not the case, then it's time to start rotating our transform around to face the target. But of course, we only really want to do that if we know for a fact that the state that's currently being executed in the animator doesn't want to use root motion. Now, we've set up our animator so that we know that's the case. We know that when the locomotion state is running, we don't want to use root rotation, but we shouldn't really write this script assuming that's the case. So if, for example, I set root rotation to 1 here because I did have a blend tree that had turning animations in it, I wouldn't want my patrol state to also be trying to rotate my character around, or we're going to get a conflict. So what we'll do is we're only going to perform this rotation behavior in our patrol state if root rotation is not currently active for the currently playing animation. And that's easy enough to get. We simply call the zombie state machines use root rotation member, which remember will just return true or false, indicating whether root rotation is being used or not, respectively. So only if we are not using root rotation are we going to step into this code and manually rotate the thing ourselves. So it's really cool because this code is going to work with or without root rotation. Okay then, so inside this conditional where we're going to start rotating Jill, what we need to do is we need to basically slowly rotate ourselves from where we're currently facing to the direction that we want to be facing. And to do that, we need to do what's called a quaternion slurp, where we rotate from our current rotation, which is a quaternion, to a new quaternion which describes the rotation we want to be facing in. So in order to perform that quaternion slurp, we need 2 quaternions. We have the first quaternion, that's simply the rotation of our transform. For the second quaternion, we need to use one of the quaternion class's helper functions so that we can create a quaternion that describes a rotation in the direction that we want to be facing. And that's pretty easy to do. We just do the following. I create a local quaternion variable called newRot, short for new rotation, and then I use the quaternion class's lookRotation function. This function takes a 3D vector describing the direction in which we wish to be facing, and it returns a quaternion from that. I pass in the nav agent's desired velocity. So we now have this quaternion which tells us exactly the direction we should be facing in. We don't just want to assign that as the new rotation of our transform because that may snap it very quickly. So what we'll do instead is we'll do a nice smooth slurp from our current rotation to this new rotation. And to do that, we get the transform of the zombie state machine and we assign to its rotation the quaternion slurp between the state machine's rotation. Actually, let me change that to zombie state machine just for consistency. So we get the transform of our state machine and get its rotation member. That's the direction we're currently facing in. And then we pass in the new rotation that we would like to be facing in. And then we pass in some sort of t value where the greater this third parameter, the more quickly the slurp is going to happen. Now, just messing around, I found that multiplying time.delta time by 5 gave a pretty good value. We don't want the slurp to be too slow, or otherwise we're going to have a pretty similar problem to the one we had when we were actually using root rotation, which is we won't rotate the zombie quick enough and we might find ourselves running into walls again. So what I'm going to do actually is I'm going to make this an inspector variable also. So I'm going to call this slurp speed, and then I'm going to go back up to the top in my variable list and make this an inspector assigned variable. So it's going to be a serialized field, once again a float, called slurp speed, and I'll just set that to 5 by default. Like I said, you want that to be pretty quick because although it might look nicer with lower slurp speeds, you're also going to lose navigation accuracy, okay? So very important thing to bear in mind. Okay, so we've now done the code that is going to rotate Jill each frame, providing that the angle isn't so great that we've dropped out into the alerted state to do a turn on spot. What we need to do now is we need to just do some tests to make sure that if the path becomes invalid or if the path is complete or any of the other things that identify to us that we're either reaching the waypoint or the waypoint is no longer valid, then what we'll do is we'll just select another waypoint from the list and make that our new target. So what I'll say is if the zombie has a stale path, for whatever reason it's become invalid or something's changed in the scene, or if the zombie doesn't have a path at all, then what we'll do is we'll just tell the zombie to go to the next waypoint in the list. And I'm going to create a function in this class to do that, which I'm just going to call next waypoint, like so. Don't worry, it's going to be red for the moment in MonoDevelop because we haven't implemented that function yet. In fact, let me implement that function now just very quickly. Private void next waypoint and no parameters, and that just gets rid of that. So what we'll also say is if the nav agent's path status doesn't equal path complete, in other words if it's invalid or partial, then basically the pathfinding algorithm was unable to find a path that took us to the waypoint, so we will just skip on to the next waypoint if that's the case. So I'm going to say if path status doesn't equal navmesh path status dot, there's the three options, invalid, partial or complete. Now we may come back and change this later. There may be times when we are interested in a partial path, but for now I'm not. So if it doesn't equal path complete, if we don't have a path, or if the path we were on is stale for whatever reason, then we will just call next waypoint. As it's just a patrolling script, it's really not that important. But for example, if we were chasing the player and the path became stale because maybe we carved something into the nav mesh or something like that, then rather than just going on to the next waypoint or the next target, one of the things that we might do is instead just set the destination again so we regenerate the path. Because just because the path has become stale doesn't mean that we can't still plot a path to that destination. But in the case of just a simple patrol stat, I'm going to say, look, if it's stale or there's anything wrong with the path, just skip it and go on to the next waypoint. And if it does mean that in some cases the zombie goes to another waypoint prematurely, it's not going to matter. If anything, it's just going to look more random and a bit more organic, and we won't have all the zombies following the same path. So that's pretty cool. And if we get past all of this stuff without any problems, then we just return patrol to stay in the patrol state. So while we're in the patrol state, and certainly in our configuration where we're not using root rotation for the animations, our zombie will be continually rotated by this code here to keep it slurping towards the desired velocity vector. So let's create that next waypoint function now, which in the case of a random patrol will generate a new random index into the waypoint network's waypoint array, fetch that waypoint and make it the new target. Or in the case where it isn't a random patrol, we will just increment the current waypoint index, making sure that we wrap it back round to 0 again if we should exceed the last waypoint in the list. So the first thing we'll do is we'll say, if this is a random patrol and there are waypoints in our waypoint network, then what we'll do is we'll make a note of what the current waypoint is, and then we'll enter a while loop that will keep generating a random waypoint until we generate a new waypoint which isn't the current waypoint that we've got set. So we don't want a situation where we tell the zombie at waypoint 3, for example, that your new waypoint is waypoint 3. Right? Otherwise the zombie will never go anywhere. So we literally just create a while loop that generates a random number. Like I said, I think that should be waypoints.count -1, because I think random range is inclusive, isn't it? Oh, it's exclusive. Okay, that's weird. I thought in the code up above it told me it was inclusive. Let me just go up to the onEnterState function a minute and just double check that, because I also generate the random waypoint up here as well. Yes, it's exclusive. What an idiot. So I don't need that -1 anywhere where we generate a random waypoint from the waypoints list. It's just between 0 and the number of waypoints. If it's not a random patrol, then we basically just take the current waypoint and increment it. So you can see we say that current waypoint equals, and then we say if current waypoint equals the last waypoint, then set it to 0, else set it to current waypoint +1. So we've incremented the waypoint with a wraparound. Okay, so at this point we have our new waypoint index, so let's just check that it's a valid index in the waypoint list. So we just say if waypoint network.waypoints current waypoint doesn't equal null, well then we will fetch that waypoint from that list and cache it in a local variable, which I call new waypoint. Remember, waypoints are of type transform. And then what we'll do is we will tell the zombie state machine that this is our new target by calling the state machine's set target function. Let me just change that to zombie state machine instead of just state machine there. Passing in, of course, the type as waypoint, null as the collider, the waypoint's position, and as the distance, we just calculate the distance using the vector3 distance function between our waypoint's position and our zombie's position. But of course, just setting this as the new target for the state machine doesn't mean we've set it as the new destination for the nav agent. So we're going to need to tell the nav agent to set a new destination and create a new path to that destination also. So we invoke the zombie state machine's nav agent property to get access to its nav agent. Then we call set destination, passing in the position of the new waypoint, and that is our next waypoint function complete. Now the next function that's pretty important for us to write is, if we look back at our AI state class, the base class, you'll notice that there is a function called onDestinationReached, and this is going to be called by the state machine for a child state whenever our zombie enters its target trigger. Now just remember this, because I know we've had a lot to take in over the last couple of weeks and we haven't really had a chance to see any of it in action. But if we look at Zombie Jill in the scene view and open up a hierarchy, you can see we have this target trigger, and we know that whenever we call set target, okay, so think of the times we've called set target just in the patrol state alone, that's going to move that target trigger over one of the waypoints. And then of course we're going to set a path to that, and the zombie's going to start walking toward that trigger. Now when the zombie enters that trigger, it's then going to inform the state machine via the state machine's onTriggerEnter function, and the state machine is going to call the child state's onDestinationReached function. So we need to implement that handler in the patrol state, because when we've reached our destination, that's when we're going to want to call the next waypoint function so that Jill finds a new waypoint to patrol to. So let me just copy the function signature so we don't have to do any additional typing, because I'll be honest, I'm pretty typed out. I'll paste that at the bottom. Change virtual to override, and you're reminded actually that the onDestinationReached function is actually called twice. when we reach the destination, and also when we are no longer at the destination. And of course, if it's called with the boolean is reached equals true, we know we've arrived at the destination, and if it's false, indicates that we were at the destination but we're no longer at the destination. And we don't really care about leaving the destination, we just care about reacting when is reached equals true. And this is going to be basically a two-line function. We're going to just return from the function immediately if we don't have a valid zombie state machine, or if is reached boolean that is passed into the function is set to false. We're not interested in dealing with the case where we're leaving a destination, only when we're arriving at the destination. So if we're not arriving and we don't have a state machine, we will just return. However, if we have reached the destination and the state machine's target type is still waypoint, then we will just select the next waypoint to go to. And the only reason I put that check to make sure that the target type is waypoint before we select a new waypoint is just because while we're in the patrol state, there is some overlap where in the last iteration we might have assigned a new target, and this function still gets called because it's still technically the current state. So I'm just building in some safety mechanisms here. Ouch. Bloody wasp just landed on me and stung me. Can you believe that? Where was I? Yeah, so I'll say zombie state machine dot target type equals AI target type waypoint. Then we just call the next waypoint function. So as soon as our zombie enters the trigger that is been centered around the waypoint, this function is going to be called. Is reached is going to be set to true, and we're just going to call the next waypoint function, which we implemented above, that is literally, in the case of a non-random patrol, is just going to increment the current waypoint index and then set that new waypoint as the waypoint target and generate a new path to that waypoint for the nav agent. Or in the case of a random target, it's going to do the same thing. It's going to set it as a target, generate a new path to it, but of course it's going to randomly select that waypoint from the waypoint list. So what I'm going to do before I carry on is I'm going to put some comments on this puppy because it's starting to all blend into one. There you go. Okay, so let's go back to Unity now and run what we've got so far. Now, this isn't going to work fully, so what I'm going to do just for testing the patrolling behavior is with Jill's AI Entity Game object selected, in the Patrol Inspector, I'm going to set the turn on spot threshold right up to 360 degrees. So in other words, we are never going to try and drop down into a turn on spot because we haven't got the facility yet to do that. We haven't created our alerted state. So what this is going to do is just have the zombie always spinning on the spot to acquire its target. And that's fine. We just want to test that everything is working okay. So what I'm going to do is I'm going to leave speed at 2, which is kind of like the jog, our zombie jog. And I think I'm going to call up the console window when we press play so that we can see the states being transitioned into. And because I think it's going to actually allow us to see things a little bit better, I'm going to really sort of look at this and see what's happening when we press play using the scene view. So when I press play, we're going to see that Jill is in her idle state, and she's going to stay there for some random number of seconds. And if you look in the console window, we should see her drop into the patrol state after the idle time has expired. And there she is. She's now patrolling. Obviously, she's spinning on the spot a little bit, and you'll see her spin on the spot a lot here because we haven't got that turn on spot idle animation. But you can see that she is basically working and she is doing her patrol. Now, because we're spinning her on the spot, that does mean that this is going to be a little bit inaccurate because we are also providing a slurp. And that slurp means that when we're traveling over a very big arc, like 360 degrees, we may have a situation where we don't turn quite quickly enough and Zombie Jill, bumps into a wall or bumps into a door, like we saw there. But don't worry, that stuff is all going to be sorted out when we put the alerted state in and have her turning on the spot for those steep angles. So it's basically working okay. She goes into the patrol state and she patrols, and you can see that if I call up Zombie Jill's inspector and then set the turn threshold down to 80 degrees again, well, let's put 90 degrees just to be safe. And what our state machine is going to do is if we try to tell it that we want to go into the alerted state and there is no alerted state, it's just going to go into the idle state by default. That's kind of like the catch-all state that we go into if the state that's been specified doesn't exist. So what you're going to see is you're going to see Zombie Jill run over to where this about turn happens in the first room, and then she's going to try and drop into the alerted state, but what she's really going to do is just drop into the idle state. So she's in the idle at the moment over there. She should start coming around the bus at us. There she is. Dun, dun, dun. If we go into that room, oh, she's in the other room. There she is, and she drops into the idle. Did actually see a little bit of a problem there. Let me run that again. There was a little bit of a glitch when she went from the running animation into the idle animation. Now I know she's not going to do that. She's going to go into the alerted animation, but I think that glitch is still going to happen. Let me get right down at her. Oh yeah, I don't like that at all. Just trying to figure out why that would be happening. Let me first of all see if I can smooth that out by selecting the transition from locomotion down into idle, because we know this is the transition that's going to be triggered when speed is set to 0 when we go into idle. And I'm going to try and just make that transition much longer. So I'll turn off fixed duration and I'll make it like a 1 second transition down into idle and see what happens. Once again, I'm going to look at this from the scene view because I think it's a bit easier to see. Here she comes. Oh, even worse. Okay, let me run that again, and this time look at the animator and try and see what's happening, why we're getting this glitch. So she's in the locomotion state, patrolling, and then we should see the transition happening. And you can see up there the blend is happening. We're seeing both locomotion and idle. I know what it is. Yeah, I know what it is. Okay, let me just put the transition back to fixed duration and quarter of a second, 0.25. Okay, so this is what's happening here, and I'm actually thinking I'm going to redesign Jill's animation state graph. You see, in our locomotion blend tree, we've got essentially 3 speeds. So if I press play, you'll see what's going on here. So we've got the walk speed, we've got the patrol speed, which was speed 2, and then we have the run speed. And it's pretty cool, we can choose between these speeds by just specifying a value into our blend tree. But you can also see that these animations don't really blend very well into each other. Look what happens there when I go into the jog from the run. There's certainly moments where those blends do not go well at all. Now what's happening is the glitch that you're seeing isn't when we drop from the locomotion state down into the idle state. It's when we're in the patrol state and we first transition into the idle state, we set the speed to 0, and of course we know that's going to cause a transition into the idle state, but the transition isn't immediate. So for at least a small amount of time we're still in the locomotion state with a speed of 0. So it's like we very quickly go poof like that. So if you imagine we were running into the room, we suddenly find that we need to do an about turn, and speed gets very quickly set to 0, and we see that very abrupt sort of lack of a blend really between the 2 speeds. Now if our animations blended better into one another, then this could be quite easily fixed by, in our animation states, instead of just saying when we go into a state we set the speed of the animator to a specific value, what we could say in the update of those states is we just lerp towards the value that state wants. So in the case of going into an idle state, what the update would do in the idle state is it would basically slowly move that down to 0 over, I don't know, half a second or something like that. And if our animations flowed into each other, that would work very well. But however, I still think we're going to get this kind of horrible effect where the animations don't really kind of work well together. And I think in this case we're going to be much better just blending straight from whatever run we're in straight down into the idle state. Now just to check that, I'm going to take our very bottom walk speed, this animation clip called 142_01. I'm just going to give that a really high threshold like 9, okay? So that basically means that our zombie run, this thing you're seeing here, is the very bottom threshold in our blend tree. So even when we set the speed to 0, it's not going to drop down to any less than this. And the reason I'm doing that is because it should emulate exactly what would happen if we just blended directly from this zombie run into the idle state, if we imagine that we didn't have a blend tree. So let's run that now and see what that looks like and see if it blends a little bit better. Like I said, if these animations blended a little bit better into each other, it would be worth implementing the lerp and having the speed slowly go down to 0. But oh, look at that, that's so much better. That's what it looks like actually without the blend tree. So I think I've made up my mind that what I'm going to do is I'm actually going to get rid of this blend tree, and I'm just going to have the 3 separate speed states and create those transitions into idle for each one based on speed. And I think that's going to be much less problematic for us. I know the blend trees are really cool, and there are going to be lots of other places where you can use them, but even when I was working on the actual Dead Earth production code, I am using a blend tree at the moment in the actual game, and I am using this idea of lerping the speed over times to try and smooth out the animations. But from the test I've just carried out, I think I'm going to just rip out the blend tree for the zombies and just use the individual states and have them blending. And then I can literally control the smoothness of the blend by just altering the transition length. And you can see that when I ran it just now, it looked fine even with just a 0.25 transition length. The point being, though, is that we have the facility to increase the length if we've got any problems. Okay, so what I'm going to do is I'm going to go into my locomotion blend tree. I'm just going to set that threshold back from 9 down to 1 again, so we have the animation clips in order of speed. So 142_01 is the walk, the middle one is the zombie run, and the one that we currently call run is the zombie sprint. So I'm going to first of all select this motion field. I'm going to lock the inspector actually so that I can call up the base layer and still have the motion fields of the blend tree available to me, because it makes it easier for me to select them in the project view. So I'm going to drag that one over, and that's our walk. I'm going to select the middle one, which is called zombie run. That's going to be our jog. And I'm going to select the bottom one, which is our sprint, which is currently called run. And then I'm going to unlock the inspector. I'm going to select each one of those, and I'm going to rename them. So this is going to be called zombie walk. This middle one's going to be called zombie jog, and this one here is going to be called zombie sprint. And then what I'm going to do, my friends, as sacrilegious as it may seem, is I'm just going to completely delete our locomotion blend tree. And then I'm going to kind of, in a way, make my own kind of mock blend tree by putting all of these states on top of each other and then creating the transitions between them manually. So let's create the transitions to and from idle for each of these states. So we know that we go from idle into walk. Once again, for all of these states, we're going to turn off has exit time. So we'll say if speed is greater than 0.1 and if speed is less than, we'll say 1.1. I mean, we know we're always going to be setting speeds to exact values. Like the walk speed is 1, so we know that if we set the walk speed to 1, then this condition will be true and the zombie walk will be triggered. And we will do the same now for zombie jog, but this time, of course, we're going to transition into that when speed is greater than 1 and speed is less than 3, which is our top speed. And we're going to transition into zombie sprint simply when speed is greater than 2. Okay, so just to reiterate, I must remember each time to turn off that has exit time, because we don't want the animation the idle animation to finish playing out its timeline before we transition. So if we're in idle and speed is basically between 0.1 and 1.1, then we go into walk. If we're in idle, we go into jog if speed is greater than 1 but smaller than 3, which we know it's going to be because we're going to set speed to 2 when we want a jog. And we're going to go from idle into sprint if speed is just greater than 2. So if it's 3 or any number above that, we know that the sprint is our top threshold. So now we need to make transitions back into idle from each of these states, and they're all going to be easy, right? Because they're just going to be, when speed is less than 0.1. We're going to be setting the speed to 0, but because it's a float, we can't use the equals. So we'll say if speed is less than 0.1, for each of these, turn off has exit time, add a condition if speed is less than 0.1, And then once again, for the sprint transition back into idle, if speed is less than 0.1. So that's going to allow us to go to and from each of our speeds, each of our locomotion speeds, and back into idle. So we probably want to make some transitions now from each of these into one another, possibly. So we'll say we go from zombie walk into zombie jog, once again turning off has exit time. If speed is greater than 1, even if it's 2, it doesn't matter. We don't want to jump straight from zombie walk into zombie sprint. If it's greater than 1, we'll just go into zombie jog. And if we're in zombie jog, that will have a test that says if it's greater than 2, then go into zombie sprint. So we'll do that now. We're saying if we're in zombie jog, then we go into the sprint if speed is greater than 2. So if speed's 3, for example. And of course, we'll do the same in reverse. Let me create all of these. And just check I've definitely turned off has exit time for all of these, because that's something I forget to do quite a bit. I have a rogue toggle set. Nope, they all look good. Okay, so I want to go from zombie jog into zombie walk. Now I can't just say if it's less than 2, because we know that we also want to transition into zombie idle if speed is less than 0.1. So we kind of want to say we want to go into zombie walk if it's less than 2, but it's not near 0. Okay, so I'll say we'll go down if speed is less than 2, and if speed is greater than, let's say, 0.9, just to be safe. So if it's nearly 1, and we're going to go from sprint down into jog if speed is less than 3, in other words, if it's 2 or 1. And once again, if speed is greater than, we'll say, 0.9, because if it's near 0, we want to go straight from the sprint into the idle. But if it's greater than 0.9, then we know it's either 1, in which case we'll just drop down into the jog and then drop down into the walk, or it's 2, which means we'll drop down from the sprint straight into the jog. And I think that's right. Okay, let's see if that gives us better behavior. I think I've done everything right there. Fingers crossed. Here we go. Should probably see what's happening here. So we should see her transition into zombie jog, shouldn't we? Because our patrol speed is 2. So there you go. Aha! Okay. It's not working, and I know why it's not working. And that's because we haven't added the state machine behaviors to these states that allow us to turn on and off route motion. So remember, when we're in our locomotion state, we want to use route position, but we don't want to use route rotation. And I think that's what was happening there. So we're going to add some behaviors to each of these. So it's the route motion configurator, which we'll add to each one of these states. And for each one of these states, we just say we want to use route position, but not use route rotation. See how flexible this system is? Great, isn't it? Okay, that should work now. Fingers crossed. Otherwise, I don't know what's going on. There you go. Now he's running fine. So if I go back to the scene view now, we should see that we don't get that jerk. Yeah, you know, she stops quite cool. Brilliant, that works fine. And you can see that it dropped back to idle. I'll just run that again so you can see the transition happening. Now, you're probably thinking at this point, hey Gary, I can't believe you spent all of this time teaching us about blend trees and then you're not even using it for your locomotion for this zombie. But don't worry, there'll be plenty of time when you can put that knowledge to good use. Yeah, and you can see it very quickly goes from the jog into the idle, and that's fine. It looked fine. So what we're going to do in the next lesson is we're going to add the alerted state so that when we get to a place where we're currently dropping to idle, we're going to drop into the alerted state, which is still going to maintain the waypoint target that it wants to head towards, but it's going to have the zombie turning left and right, trying to find the direction that it wants to take to go to its target. So before we go, we're just going to have a little bit of fun with one last little function that we're going to implement, and that's going to be messing around slightly with our ability to override the onAnimator IK function in MonoBehavior where we can set some of the IK goals for some of the body parts of the humanoid avatar. And all I'm going to show is the most simplistic case, where what we'll do is we'll have the zombie, as it's running to its waypoint, we'll make sure that its head is turned generally in the direction of that waypoint. So that should be pretty cool. And of course you can use this whole IK goal thing for hands and feet as well, but we're just going to use it in the short term at least for the head. Now fortunately, because we're using a humanoid rig, it makes this delightfully easy to do, because the fact that we're using a humanoid rig means that Unity knows where the head is on our model, it knows where the hands are, it knows where the feet are, so it has special functions that allow us to tell Unity where we want to place those hands, where we wish the head to look, just before the IK is resolved. So the way it basically works is, if we go back to our AI state machine class, which was derived from mono behavior, you will remember that we wrote a function which we're yet to use called onAnimator IK. This is one of Unity's magic functions, and it is called by Unity and gives us a chance to set some of the targets of those humanoid goals, like the hand, the feet, and the head. And all we do is we trap this in our state machine and then pass it down to the current states onAnimator IK updated. So all we have to do in our patrol state is override this function from our AI state base class, because in the base class I think it just has an empty function body, there it is, and do something with it, and it's going to be 2 lines of code. So we can say that this is the direction that we wish the head to generally look in, and this is the weight at which we wish to blend that with the original direction that the zombie is looking in the animation. So what I'm going to do is I'm going to copy and paste this onAnimator IK updated function from our base AI state class, and I'm going to copy this into the very bottom of our patrol script. Save me typing all that out again. And I'm going to change virtual to override. Okay, so here we are now in the onAnimator IK updated function. It takes no parameters, so how the hell do we do something with this? Would you believe me if I told you that the animator has a function called set look at position, specifically for allowing us to tell the humanoid rig where we want its head to look? Well, my friends, that's exactly how easy it is. So we better make sure we've got a valid state machine. So we'll say if zombie state machine equals null, then return. Else we will say zombie state machine dot animator dot set look at position. Oh, and look, and there's the other function we're going to use, set look at weight. So where do we want to look? Well, we just want to look at our target, don't we? The current waypoint, I guess. Or in fact, whatever target we've got set. So we'll just say zombie state machine dot target. Oh, I've just noticed I don't have a way of getting the currently set target. I don't have a getter in the zombie state machine. Yeah, I should probably create a property that allows me to get the currently set target's position. So I'll implement that in a minute. So you can see I just say zombie state machine dot target position, and then if I go back to our AI state machine class, I'll put it in the same place that I added the get target type property earlier on here. So I'll create a public property that returns a vector3, and I'll call that property target position. It has a getter that simply returns the position of the currently set target, like so. So now when I go back to my patrol class, that should no longer be highlighted red. And then we want to set the weight that we wish to blend this command, if you like, in with the direction the zombie is looking, based on what it should be doing in the animation. So we'll do like a 75% blend. So I'll say zombie state machine dot animator dot set look at weight. That's just a value between 0 and 1. So we'll say 0.75, right? I mean, we could make that an inspector variable, I guess. Okay, so let's give that a run and see if we can see Jill's head looking in the general direction of her waypoint when she starts running. Now we're only going to see this in the patrol state, not in the idle state, because in the idle state we're not doing this this set look at position. Nope, that's not working, is it? Her head isn't looking at the waypoint. Definitely not. Okay, so let's do a little bit of debugging. Let's go into the onAnimator IK updated function. Let's put a debug log in there and just check that this function is being called by the state machine. So I'll say IK goals being set. Boeing. There you go, being set, not Boeing set. Press play again, and if we don't see that debug text being printed to the console window a lot every frame, then we know we've got a problem. Okay, so our function isn't being called, and I've just remembered what that is. Okay, this is an easy problem to fix. If we go back to Jill's animator, I've just remembered that on a per layer basis, you have to specify whether you wish an IK pass to be done on that layer. So with the base layer selected, go to the little cog on the base layer, and you can see there's a little toggle there called IK pass. Tick that on, and you'll see there's now a little IK on the base layer. And I'll bet you a bottom dollar that if I run that now, her head will be firmly yoked around to the right when she starts running, looking at that waypoint. Yeah, definitely. There you go. See her head looking? And now she should be looking to, yeah, she's sort of looking into the room before she even gets there. Okay, so probably the only problem I would say with that is the blend is a little bit strong. Maybe I'll put it down to maybe 0.55. I'll remove that debug log. And I think another problem that we've got, and it doesn't notice quite so much here, but it certainly is going to notice in the pursuit state when we use this code again to have the zombie looking at the player when it's running towards it. And that's that most of the targets, such as our waypoints, are on the floor. So when we set the head to look right at the target, even if in the case of the player where the game object's origin is normally kind of at the waist or at the feet of the player, when the zombie's running at us, it will be moving its head and rotating its head to look at us, but it's going to be looking at our feet. So a pretty quick fix to that is when we're setting the look at position, we'll just add a unit length up vector to that. So we'll say vector3.up. So we'll say wherever the target is, we just want you to look 1 unit up from there, 1 meter up. And I think that should probably work just fine. Clear the console, press play. Let's see her coming around the corner because it'll be a bit easier to see. Yeah, that looks better. See her head looking there? It's already looking into the room, intending where she's going to go. Okay, well, I think we've accomplished quite a lot in that lesson. I am going to add some comments on that onAnimator updated function. And I think I'll just say override IK goals. Not very descriptive, I know, but we know what that means. So you've just seen how easy it is when we're using a humanoid rig to actually tell Unity that we want the head to look at a very specific target. And like I said, doesn't really make that much sense in the patrol state, but when we're in the pursuit state and we've got the zombie running or sprinting at the player, it's going to be much more convincing if when it's running at you and it's running around obstacles, its head is still sort of fixed on its target. That's going to be pretty frightening when it's running at you in that way. So that is our patrol state done. And I'm going to leave it there, and I come back in the next lesson, we're going to add the alerted state, and we're going to see our zombie reaching its waypoint, dropping down into the alerted state, and panning left and right. And when we add the alerted state, we're also going to be able to start messing around with creating some mock threats. So we'll create like a sound emitter, and we'll see what happens to Jill when that thing goes off in her sensor trigger. Okay, well, thanks for listening, guys. This has been Gary Simmons of the Game Institute. I'll see you next time. Bye-bye now.